Hello, my dear children. Welcome back. I know. Your exams are just around the corner, and this chapter, alternating current, can feel a little tricky, isn't it? But don't you worry at all. Today we're going to make it super simple for you. So, are you ready? Let's begin.
So just relax, take a deep breath, forget all that exam tension. Trust me, by the end of this little session, you'll feel so confident about AC. That's my promise to you, okay? So, let's jump right in. Okay, first things first. What exactly is this alternating current? AC. You've already learned about its cousin, direct current, or DC, in your earlier classes, right? Well, AC is the one that's a bit more famous, you could say. It's the current that's powering everything in our homes right now. So what's the big difference? It's actually really simple to picture. Imagine direct current. DC is like a car driving on a perfectly straight road. It just goes in one direction, steady and constant. But AC? Oh, AC is more like a child on a swing, a jula. It goes forward, then backward, always changing direction. See? It moves just like a wave, going up and down, up and down. Now you might be thinking, and this is a very clever question, Sir, if the current goes forward and then backward, doesn't it just cancel itself out? Right? If its average value over a full cycle is 0, then how on earth does it light up a bulb or charge our phones? That's a brilliant question. And the answer brings us to the real hero of this chapter. And our hero is the RMS value. Now, don't get scared by the big name, root mean square. Just think of it as the effective value of AC. It's like asking, what's the DC equivalent that would give us the same amount of power? You see, the magic is in the heating effect. Whether the current is positive or negative, when you square it to find the power, the result is always positive. That's the secret sauce. So it's always delivering power. And here's something super important for your exam, beta. Please pay attention. You know the 220 volts we get in our homes? Well, guess what? That is the RMS value. The actual peak voltage, the highest point that wave reaches, is much higher. It's actually the RMS value multiplied by root 2. Which comes out to be around 311 volts. Wow, please remember this. It's a very common one-mark question they love to ask. All right, so now we understand what AC is. But what happens when we put it into a circuit? Well, AC has 3 best friends it loves to hang out with. And each friend has a totally different personality. We have the simple, obedient resistor, the kind of lazy inductor, and the super energetic capacitor. So let's meet friend number 1, the resistor. He's the simple, no-drama friend, super obedient. Whatever the voltage does, the current does the exact same thing at the exact same time. If voltage goes up, current goes up. Voltage is at its peak, current is at its peak. They're like best friends walking hand in hand, perfectly in step. In physics, we have a special term for this. We say they are in phase. Next up, meet the inductor. Now, this friend is a little lazy. He really dislikes change. So when the voltage comes along and says, hey, let's get this current moving, the inductor says, do we have to? It resists that change. And because of this laziness, the current always ends up falling behind the voltage. It lags behind by exactly 90 degrees, or pi by 2 radians. Now, this special kind of opposition from our lazy friend has a special name. It's called inductive reactance, and we write it as XL. And here's the thing to remember. The faster you try to change the current, meaning the higher the frequency of the AC, the lazier and more stubborn the inductor gets. So more frequency means more opposition. Inductive reactance increases with frequency. And finally, our third friend, the capacitor. She is the complete opposite of the lazy inductor. She is full of energy. A capacitor just loves to charge up and discharge. Charge and discharge really fast. Because of all this energy, the current gets super excited and rushes ahead of the voltage. So, in a circuit with a capacitor, the current always leads the voltage, again by 90 degrees. And you guessed it, her opposition also has a name, capacitive reactance, or XC. But here's the twist. Because she's so energetic, she actually loves fast changes. So the higher the frequency, the less she opposes the current. It's the complete opposite of the inductor. For a capacitor, more frequency means less opposition. It's an inverse relationship. Okay, so we have lagging, leading. It can get confusing, right? Especially in an exam. So I have a super simple trick for you. Just remember one word, civil. That's C-I-V-I-L. What does it mean? Well, in a capacitor, C, the current I comes before the voltage V. And for the second part, in an inductor, L, the voltage, V, comes before the current I. See? Civil. You will never forget it now. All right, so we've met all the friends one by one. But what happens when they all get together? When the simple resistor, the lazy inductor, and the energetic capacitor all team up in one circuit connected in series? Well, that's when we get the famous LCR circuit. Now, when these three are in a team, things get interesting. Their effects don't just add up simply. You have the lazy inductor pulling one way and the energetic capacitor pulling the exact opposite way. It's like a constant tug of war between them. And this creates a total opposition that's a bit more complicated than just simple resistance.
We call this total combined opposition from the whole team impedance, and we use the letter Z for it. The formula for impedance takes care of everything. It includes the resistor's simple opposition, and it calculates the winner of that tug of war between the capacitor and inductor. That's why the formula looks like Pythagoras' theorem, right? It's not a simple addition. This formula, beta, is an absolute must-remember for your exam.
Okay, enough theory. Let's solve a real question, the kind you might see in your board exam. So imagine we have a resistor and a capacitor, and they're hooked up to a 220-volt source. The question asks us to find the current in the circuit and the voltage across each component. So, how do we even begin? Don't worry, it's just a step-by-step process. First, we'll calculate the capacitive reactance, XC. Easy. Then, we use our formula to find the total impedance, Z. After that, we can use a version of Ohm's law, I equals V over Z, to find the current. But here's where it gets really interesting. A little paradox. If you then calculate the voltage across the resistor and the voltage across the capacitor and add them, you'll find the sum is more than the 220 volts we started with. How is that possible? Is it magic? No, it's because they are not in phase. Remember, they are not pulling at the same time, so you can't just add the numbers. You have to add them like vectors, using Pythagoras again. Okay, now for what I think is the most magical part of this whole chapter. It's called resonance. You know, beta, everything has a favorite frequency. Think about a jula, a swing at the park. If you push it at just the right moment, with just the right rhythm, it goes higher and higher with very little effort, right? That's its natural frequency. Well, an LCR circuit has one too. At one very special frequency, which we call the resonant frequency, something amazing happens. The opposition from our lazy inductor becomes exactly equal to the opposition from our energetic capacitor. Their tug of war ends in a perfect tie. They completely cancel each other out. So what's left? Only the simple resistor. The total opposition, the impedance, is at its absolute minimum. And when opposition is minimum, what happens to the current? It shoots up to its maximum value. This is the magic of resonance. And it's not just theory. It's exactly how you tune your old radio to catch your favorite station. So, to finish up, let's answer a big question. Why do we go through all this trouble with AC? Why is it everywhere? The number one reason is a truly amazing device called the transformer. This is the gadget that lets us easily step voltage up to very high levels or step it down to very low levels. And that ability is absolutely essential for sending electricity efficiently over hundreds and hundreds of kilometers, all the way from the power plant to your house. And they come in two flavors. First, you have the step-up transformer. It has more turns of wire in its second coil than its first. And as the name says, it steps up the voltage. They use these at the power plants for long-distance travel. Then, near our homes, we have the step-down transformer. It has fewer turns in the second coil, and it steps the voltage way down to a safe level for our appliances. The rule is just so simple. More turns, more voltage. Less turns, less voltage. That's it. Okay, beta, quick revision time. Let's lock in these key points for the exam. Ready? Resistor, simple friend. V and I are in phase. Inductor, lazy friend. Current lags. Capacitor, energetic friend. Current leads. How to remember? Just say civil. The total opposition for the team, that's impedance, Z. And the magic moment, resonance. That's when impedance is minimum and current is the king. You've got this. See? What did I tell you? It's not so difficult after all. You have totally got this. You've mastered alternating current. So now the next time you flick on a light switch or plug in your phone to charge, just take a second and think about this amazing, beautiful dance between voltage and current happening inside those wires. Physics is just magical, isn't it? Please study well, Beta, but don't take any stress. You are going to do wonderfully. All the very, very best for your exams.